Thanks so much, Melissa, for the kind introduction. And I also want to thank you all to join at such a late hour. As you will see with me, I rarely have short titles or short papers, unfortunately, but I'm working on that. As Melissa said, this is recently published in Minerals in the special VMS issue, edited by Steve Hollis, with Jonathan Cloutier, as well as Jean-Luc Pilote. And I will share my presentation now. As said, this is about a greenfield exploration target in north central British Columbia called the A6 Anomaly, and will provide here some data on stratigraphy, lithogeochemistry, as well as alteration, mineralogy, and chemistry to decipher or constrain if it has potential for VMS mineralization. Before I dive in, this research would have not been possible with the work and contribution and support of my co-authors, namely Craig Johnson, who did his honors thesis on the alteration, as well as the support of Stefanie Waythorn, Christina Ensley, and Ken McNaughton from Bridium, and Harold Gibson and Ross Sherlock from Laurentian. This work is also part of my postdoc that I did with Merck at Laurentian. So as I said, the A6 Anomaly is a greenfield exploration target in the Golden Triangle, and those of you who work out there know it's quite hot right now for exploration. So a lot's going on. The reason why the A6 Anomaly, this area in particular, was targeted is it's not only close to the epithermal Brueckner mine, it also, as you will see, has some characteristics of the Eskay Creek deposit, which is the most gold-rich VMS deposit known today. And based on the drill core data I will present to you, the objectives of the research was to constrain the VMS potential using whole rock lithogeochem, particular on the felsic and mafic units, as well as provide a preliminary tectonic setting and compare the A6 Anomaly to the Eskay Creek to decipher to what extent it may host the VMS, economic VMS deposit, and I will present that in the first part. And then we also looked at the felsic units that are altered and used the alteration, mineralogy, and chemistry to constrain the hydrothermal fluid conditions, and this is presented in the second part. I also want to highlight this is really a greenfield exploration study, so the data presented are limited to 10 drill holes that were logged and analyzed in 2019 and 20. So those of you, one second here, those of you who aren't too familiar with the geologic setting of Western Canada, we are here in the Cordillera, roughly 1,500 kilometers north of Vancouver, and the Western Cordillera are made of roughly north-south trending terrains, of which this decline or Stikinia terrain here in the forest green is the longest within the Canadian Cordillera, have predominantly Jurassic age, formed both in an arc and failed back arc setting before it docked on to Laurentia and especially here Cache Creek deposit. The A6 Anomaly itself, this is a simplified map, is on the west side of the Bowser Basin, which is the highest stratigraphic unit here. And I will get back to the stratigraphy in a second. But the A6 Anomaly is very close to the KSM and Brueckner camp, so Kerr, Sulfurets, Mitchell. These are all, including Brueckner and Snowfields, these are all mines and deposits of the so-called Lower Hazelton group, namely in the Betty Creek Formation. So these are lower Jurassic age arc assemblages that host porphyry showings or in the form of Brueckner epithermal one. And then, of course, we have here Eskay Creek, which is much younger in age, part of the Upper Hazelton group, roughly 174, 175 million years old based on age data from cuts. And the Eskay Creek deposit always attracted a lot of people because of its unique characteristics. And studies showed that the Eskay Creek most likely formed in the so-called SK rift, which is a north-south trending structure that also holds the Antioch deposit. And when we looked superficially at the A6 anomaly here, there were superficially some characteristics that were very similar to SK Creek, which I get into in a moment. The terrain, those of you who's working there, is very rugged, only helicopter access, and it's between 1,200 meters here in the depression, so retreating glacier, and then on the flanks up to 1,600 meters. And the drill holes that were set and are part of this study are fairly wide space just to see what's going on. And you will see that I refer throughout the tour quite a bit on the terms on the flanks, which is here west and east side, and then retreating glacier, simply because the stratigraphy differs a little bit in these two regions. The next thing I will show you is a cross-section of A to A prime here from west-northwest to east-southeast, based on several of those drill cores that I logged and analyzed. So we're going into part one right now. So the lithogeochemistry is based on the core logging I did. And the age relationships between the section here at lower elevation beneath the retreating glacier and the flanks is not easy to establish. And that is because of limited drill core data. We don't really have a structural picture of the area, and the age data are a little bit ambiguous, I should say. So we have here the retreating glacier, and orange are the felsic flows, have age of 172 million uranium lead zircon age. And then the flanks, both an epiclastic unit as well as a volcaniclastic unit, are slightly older. However, I interpret those ages as a more maximum age, and hence, based on the age relationships and cross-cutting relationships I see, I think that actually the footwall of the whole package here at A6 are those felsic flows in orange that have minor volcaniclastic rocks, and will be part of the talk here. We have some alteration as well as pyrite mineralization. And then overlying are these rocks by a turbiditic sequence that is very nicely graded, ranges from conglomerates to siltstones, and they intercalate with these green units that are aphanitic basalts. You will see geochemically they are different to the dark green basalts that are more prominent on the flanks. What we have on the flanks as well, besides those so-called group A basalts, is that they alternate with mudstones. We don't see much mudstones here under the retreating glacier. We see it much more common on the flanks. And that could be also, as you will see, the highest stratigraphic unit, because those mudstones have characteristics of the quark formation, which is the highest part of the upper Hazelton group. And then we have cross-cutting darks here in purple. But the focus, and you will see this is why those different colors coming back, so you can follow it, are the green and the orange units, so the basalts as well as felsic flows. So when we look at the altered felsic flows, they are very massive. They show sometimes flow bands, and under microscope, they have also a really nice pylitic texture sometimes. We have weak to moderate alteration of dominantly quartz and sericite. I dive into that in the second part of the talk. Sometimes pyrite stringers, but no abundant or high mineralization or any high metal assay data. Overlying is this unit by these turbidites that have siltstones. The green arrow is stratigraphic up. So these fine siltstone with these fine to coarse-grained sandstone bands. And then we have pebble conglomerates that have polymictic clasts of both igneous as well as epiclastic composition. And then we have intercalated with the turbidites, often those group B basalts. They are geochemically different from the group A, not necessarily in the field. You can't distinguish them very well there, but geochemically, as you will see, they are different. They are often amygdaloidal or aphanitic. And then we have higher up in the stratigraphy, the group A basalts, which can also have, besides a massive and amygdaloidal texture, a pillow texture with these nice quenched rims, as well as those amygdals here. Interestingly is that those group A basalts, as I grouped them based on geochemistry, are often reworked and form in situ hyaloclastides. Here you see really nicely those pillow basalt fragments broken up. And those group A basalts are also intruded in the overlying mudstones when the mudstones weren't consolidated yet, forming really nice mudstone basaltic contacts in the form of peperites. And then higher up, we have those mudstones with those typical pajama beds that are very common in the region and a good sign of the quark formation, which is much younger than the rhyolites. And this is also why I put the stratigraphy that way, from the footwall, relatively footwall rhyolites overlying by the turbidites and the basalts, and then going into the mudstones. And then, of course, we have the mafic dikes. The mafic dike 1 are cross-cutting all lithologies. They can be fairly thick, and they are, I'm not showing that here, I just want to mention it, they are very similar to the group A basalts. And then we have an alkali basalt dolerite dike that is more prominent in the retreating glacier area. And even we didn't date it, but they seem to be very common throughout the region and maybe of tertiary age. So, because I will come back to SK Creek quite a bit, because that was also to see if we have something similar to SK in the region. When we looked first on the surface at A6, we saw quark formation intercalated with those pillow basalts. That's very similar to what we have in the top of stratigraphy of SK Creek. However, after core logging and looking more in detail at the lithologies and chemistries at A6, there are significant stratigraphic differences between both locations. Namely that in the footwall, we do not have any sediments below the felsic flows. I have to say, though, that this is not very well defined, because there are only 2 holes that really went through the felsic flows itself. So there's more work to be done, what's underlaying. There might be Betty Creek there at A6, but it's not very well defined. The felsic flows have a similar age. The A6 is slightly younger than the SK rhyolite. As you will see, they are geochemically, however, very, very different. What's also different is really the hanging wall above the rhyolites, where we have a turbidite sequence, as I just showed, with different basalts intercalated with it, whereas at SK Creek, we have a constant, very thick mudstone package intercalating with those basalts, partly pillow basalts, that are uniform in their geochemistry, and also those mudstones are often mineralized with this typical sulfur salt realgar mineralization. So even stratigraphically, we see differences. The question now is, what does the geochemistry say? And I plot here for comparison always the data, both of the felsic as well as the mafic units from Sherlock, or from Barrett and Sherlock in the mid-90s, from SK Creek in yellow. The Skinner Resources, who owns SK Creek at the moment, was so kind, provided samples as well, both for the rhyolites as well as the basalts. So these data are here for comparison. And if we do a simple Pierce plot to just see what's going on, as well as Ross and Bedard to look at the affinity, the A6 felsic flows are much different. These are calc alkaline, low zirconium, rhyodacite to trachites. They have higher titanium, but lower high field strength elements compared to the tholeidic rhyolites that have up to 400 ppm zircon at SK Creek. So here's a difference that also indicates that there happens different source regions, most likely also different tectonic settings, and I'm coming back to that in a moment. The rare earth element pattern here relative to primitive or normalized to primitive mantle differs also between two locations. We have a slightly decreasing light rare earth pattern with a flat heavy rare earth and a very weak europium anomaly at A6 compared to overall relatively flat rare earth element pattern at SK with a very prominent negative europium anomaly indicating plagioclase fractionation in the precursor. So if we look now at the mafic units, as I said, at A6 there's more diversity, and it's actually a very interesting story, because if we look at the group A basalts, which were these pillow basalts really high up in the stratigraphy that form those pillows as well as intercalated with the mudstones in the dark green upside down triangles. These are your typical tholeidic basalts with a very low neob-ytterbium ratio, very low zircon, and varying magnesium number up to 70. They are also very similar geochemically to the hanging wall basalts here in the diamonds as well as the square at SK Creek. However, then we have those group B basalts that overlie the rhyolite flows in the retreating glacier area, and they are more transitional to calc alkaline, have slightly higher zirconium concentrations and lower magnesium numbers. So again, indication that something else went on for those two rock types tectonically. And that is also shown here in the rare earth element pattern relative to the SK Creek hanging wall basalt. Again, the group A basalts overlap quite nicely with slightly declining light rare earth element pattern, but overall relatively flat, no anomalies, compared to the group B basalts, which have a very steep pattern in the light rare earth elements and then flatten out towards the high rare earth elements, heavy rare earth elements. So now that we characterize the lithogeochem of both the felsic flows as well as the basalts, it's a question, okay, how do we apply these data to constrain a potential VMS prospectivity? And those diagrams are well used here on top. We use trace elements and ratios of them to characterize the fertility of the flows based on Lesher in the mid-80s, as well as from Hart et al. In the early 2000s. And what you see is that actually A6 anomaly is typical calc alkaline F2 minor F1 rhyolite. A lot of VMS systems are F2 rhyolite hosted. But as you will see in the lower diagrams, unfortunately, the F2 rhyolites at A6 are not very well zirconium enriched and are more I-type granite similarities so formed in a volcanic arc and overlie when we use data from Piercy in the late 2000s, more with VMS systems that are barren of any mineralization. In contrast, the tholeidic F3 rhyolites at SK Creek, of course, we know they are metal bearing. It was mined in the early 2000s, but they have also a higher range of zirconium and plot in this anomalous ocean ridge within plate area that's also typical for other VMS systems here in dark gray that are actually ore bearing. And that also indicates that at least the felsic units may not have had the potential for mineralization. Many VMS systems are associated with mafic rocks, and they tell us a good history as well of the tectonic setting. Hence, they are often used as well for indication of VMS potential. So when we look here, again, of the group A basalts that are very similar to SK Creek, here SK in brown and in dark green group A basalts, they plot in that BABB back arc basin basalt field relatively low titanium-vanadium ratio. And if you use the Pierce plot here, we see they have an N-MORP affinity that's typical for a lot of mafic rocks that are associated with ore-bearing VMS, bimodal VMS systems. In contrast, the green group B basalts have a much wider ratio of titanium-vanadium concentration, more an E-MORP affinity. And if we look what kind of crustal contamination took place in both group A and group B basalts, we actually can again use Pierce from 2014, and they're here modeled if either the N-MORP or the E-MORP was contaminated with the upper continental crust of Gao and Rudnick, or Rudnick and Gao. Of course, this is a very mature end member. You could use a less mature end member, would get similar results. Those mixing lines here show you the increments of the crustal components. So the closer we are to UCC, the more crustal contamination we have of either the N-MORP or the E-MORP source. And what's shown is that especially the group A basalts have relatively low crustal contamination. SK Creek has almost none. And then we have more crustal contamination, and that's also backed up by the other geochem data I just showed in the group B basalts. And if we use Cabanas and Lecol's tectonic diagram, we see again very different settings of a more calc-alkaline setting for the group B basalts, where we are in the backup or transitional arc environment for the group B basalts. So before I dive into potential implications for the tectonic setting, I just want to summarize the sorry guys, it has been a little bit late. I want to summarize the lithogeochem results for the prospect at the A6 anomaly and deposit, VMS deposit at SK Creek. They differ significantly in the felsic units because we have calc-alkaline of 2 rhyodacite to trachytes, indicating a melting source of more than 10 kilometers, as well as quite a bit of crustal contamination, because we have low zirconium contents, and they are similar to I-type granites. In contrast, the tholeidic F3 rhyolites at SK indicate a shallower melting source. We have a significant negative europium anomaly, so we know the precursor underwent plagioclase fractionation. We have higher zircon contents, and the rhyolite also resembles A-type granites. Of the mafic units, we have a more diverse picture at A6, where the group A basalts are very similar to the tholeidic hanging wall basalts at SK Creek. Both have very low niob-ytterbium ratios with flat RE patterns and an N-MORP signature, whereas at A6 we have a weak crustal assimilation as well. In contrast are the more calc-alkaline group B basalts with higher niob-ytterbium ratios, very steeply declining rare earth patterns, have more an E-MORP signature with a stronger crustal assimilation. And from the tectonic setting, as I said, SK Creek is put in this back arc basin that developed into a rift where we had shallow melting and created both the tholeidic rhyolites and the hanging wall basalts. At A6, we most likely have a more complex tectonic history where there is a back arc basin, but it's just evolving into a rift, which I show here. I apologize for the very simplified sketches, but based on the data, I wanted to keep it as simple as possible. So we most likely had first the beginning of a rift system, but the melting was still fairly deep, over 10 kilometers, creating those calc-alkaline F2 rhyolites, as well as the group B basalts that assimilated quite a bit of crustal material. And then they came in with some, especially the basalts, had some turbidites, because we had an active tectonic setting going on. With ongoing thinning, the mantle upwelled even more. So we had shallower melting at less than 10 kilometers with less crustal contamination, creating here in darker green the group A basalts that also intercalated with those mudstones of the quark formation that symbolized the docking of Stikinia to Cache Creek. Please also note here the time, fish is still there, and then later fishy made it over the rift. So if we compare the lithogeochemistry and the A6 anomaly based on the lithogeochem data does not show too much indications that there is a mineralized and economic relevant VMS system present. It's most likely a barren VMS system. However, the tectonic setting is implying that we have an evolving back arc basin in a sub-basin that has not been identified yet east of SK Creek. So the SK rift has been often very straightforward put as a north-south trending structure based on the basalt data we have there, and not much has been done east of it. And if you look at this simplified geologic map, everything in the orange tones is this Iskit River formation that hosts both SK Creek and A6. So it would be really interesting if people could look for further exploration targets and define other sub-basins that may have more tholeidic rhyolite signature. Maybe there is a tholeidic rhyolite at A6 anomaly and we just haven't drilled it yet or found it yet. Because keep in mind that there were only 10 drill holes done. So it's really important to do more exploration work in that area. So I now want to go to the alteration of the felsic flows, and this is the work mainly by my BSc student. And even we knew it was most likely a barren system, the alteration chemistry really helped to define the hydrothermal fluid conditions because the felsic flows are altered. So we know something was going on. And if we look at the alteration of those felsic flows, it's pretty straightforward. We have quartz with cerussite in form of illite, minor potassium feldspar, and traces of chloride, pyrite, calcite, as well as barite and rutile. And the felsic flows often have these really nice plagioclase phenocrysts that often strongly replace, by cerussite. It also can replace the matrix quite a bit. And we have also plagioclase pseudomorphs with a quartz core and potassium feldspar rim here. And this is an SEM picture based on elemental maps. So this is all the same grain. And here you see again the alteration of plagioclase to cerussite because we have here some potassium going on. And then we have also some replacement of that pledge. It's not very common, but it's a really nice example here of pyrite because the core is already with these nice pyrite crystals. We put a paragenesis of the alteration in. We have the primary feldspars and quartz. The feldspars, especially albite, minor plagioclase is replaced by illite early on. Quartz is also an alteration phase. We have minor potassium feldspars alteration, and then secondary late stage, most likely lower temperature, calcite as well as barite alteration. It's not very common. The XRD results showed that very clearly though. So Craig analyzed over 100 grains to define what composition the cerussite had, and using microprobe. And the different samples showed a very wide variations. Those of you who are not too familiar with that plot, it's I think from Welde, and it's using the composition of very common clay and alteration phases to decipher what's the composition of the clays, including silica, all in atomic formula per unit, the interlayers on the M side, and then on the R side here, the octahedral iron, magnesium, and manganese composition. And the data of the analyzed ylides are here in this open blue circles that are all overlapping, and then are end members of known clay minerals, including muscovite, montmorillonite as a smectite family member, pyrophyllite, ylite, and fangite. And this gray triangle is shown here again, and it shows the widespread of the analyzed xerosite much better. And you see that we have actually wide variation of ylite with 0.65, 0.6, or 0.88 potassium per fermular atoms per fermular unit. And ylite is an interesting mineral because it can form interlay or mixed layers with smectite, hence montmorillonite. But the higher your potassium content is, the more you are closer to the ylite end member. So we see a clear trend from an ylite smectite mixed layer, so with low potassium per formula unit, to a more end member ylite. We do not reach muscovite, and we do not have any fangite component either. And that tells us a lot about the temperature range, at least we have. So ylite smectite is more stable around 200 degrees, where muscovite and ylite are not coexisting with each other above 260, 300 degrees. So we know already, okay, we are here under 300, maybe even below 260 degrees. So I'm going a little bit back, and I'm coming back to those ylite composition a little bit later again. But we know that from the mineralogical and XRD data that a lot is going on alteration-wise, and we back that up by mass balance calculations of these altered flows using a single precursor based on loss on ignition, AI, as well as xerosite index. And we have clear feldspar destruction, similar what we see. We have a loss of sodium here in percent, almost 100% in some cases. We also have strong increase of potassium, indicating the ylitization of the feldspars, and minor development of carbonatization. We have here an increase in calcium. We have some minor chloratization. Pyritization, this is an outlier. It's not very common, but we have it here and there. And then, as said, we have some barite formation, which is very minor. And depending if we have a strong silicification, we have gain in silica. But if we have also a strong feldspar destruction, we lose some silica as well. So all those data, the ylite data, as well as those mass balance calculation, plus the stratigraphic data, show that the rhyolitic or rhyodicitic flows are actually altered to xerosite. So we have a typical xerosite alteration in the footwall. The limited amount of data didn't allow to constrain any halos. So we don't see any chloride halos that are more common in VMS systems. So it's a pure xerosite alteration of those felsic flows. If we look into the ylitization a little bit more, what caused it, and here we come, how we can use the data to constrain fluid conditions. This is a very common box plot after large with the alteration index versus the chloride carbonate pyrite index. And from the precursor, we move clearly into the feldspar and muscovite area due to the ylitization. And we have actually ylitization in 3 processes. And that is very well seen on the smaller plot by Davis and Whitehead, where we have dominantly a sodium loss and a potassium gain because we destroy albite. And we can plot that on an activity diagram after Inouye. And we see that if we destroy albite and form ylite, and that's also expressed in that equation, we need an acidic component or acidic fluid that's also mildly oxidized. Then we can have ylitization of plagioclase as well, as where we have both sodium and calcium loss, but potassium gain as shown here in that pathway. Again, acidic conditions, mildly oxidized. And then finally, not very often, but we can actually alter potassium feldspar as well to ylite creating again illite by destroying feldspar due to an acidic fluid again. So, and this is this pathway. So combining all these data and our knowledge of the mineralogy, the illitization of dominantly pledged and albite was due to acidic, mildly oxidic fluids. We know it happened below 300 degrees, most likely below 260, due to the stability of illite end member and no muscovite. But I try to, or we try to decipher the fluid temperature further, and we used two approaches. One was oxygen isotope composition of illite and quartz, and they overlap quite a bit. So here we have, again, illite completely replacing a pledge, and the composition is shown in blue. And then we have neighboring quartz here in the orange dots. Same image here, fine illite replacing some of the ground mass, and then quartz nearby. Illite have an average composition of 10.7 relative to Vienna standard mean ocean water. Quartz is slightly higher. We use different approaches to see if there's any, if we can calculate the temperature. However, illite and quartz are not in equilibrium, so this pair in itself won't work. But what we could use is, because the formation of illite and quartz as alteration phases was due to the fluid phase, we could use the illite water and quartz water pair. And these are very well defined systems, as well as from a thermodynamic standpoint. And those of you who worked with oxygen isotopes and evolved seawater know that it's usually slightly higher than 0 per mil. But when we use the composition for the hydrothermal fluid of 0.5 per mil for illite here and quartz here, the temperatures were very low, below 170 degrees. This is not what we see from the illite composition. So we use two different compositions of 2.3 as reported from other systems, as well as 4. And that's reported both from the modern seafloor, like Melissa's work, as well as from Kuroko, indicating also that there could be a magmatic component to this higher oxygen composition. However, if we use 4 per mil for the fluid in combination with illite or quartz, the average temperatures are very well representative of our illite composition, around 220 to 240 degrees. But they also overlap with the illite geothermometer after Patalia. This is quite controversial in some deposits, but it works very well here using the illite composition and this formula, giving a temperature of roughly 225 degrees. This, again, really backs up all the data we see from the alteration samplage, from the data I just showed on how the illitization happens, etc. Interestingly, though, is if we have really an oxidized, mildly acidic fluid between roughly 2 to 250 degrees, so I give here a little bit of leeway, we should transport lead, zinc, and precious metals very well. This is ideal conditions for those metals. Problem is, we have maximum a few hundred ppm zinc here and there, and no real enrichment in gold and silver. So the metal transport was inefficient. Is this due to a barren source, or is this because we are so distal to a potential VMS deposit? We cannot say that. Interestingly is also that actually the fluid temperatures at A6 are much higher than at SK Creek, which is below 200 degrees based on fluid inclusion data from Sherlock et al. In the late 90s. So summarizing the alteration is that we have a sericite alteration in the felsic flows at both locations. However, it's much more weaker at A6, represents a footwall there, maybe a distal footwall, because we can't really see alteration halo yet. It was the only alteration identified. The main Cerussite phase is illite, formed by oxidized mildly acidic fluids up to 200, 250 degrees, forming, however, uneconomic pyrite stringers with no economic assays of zinc, lead, gold, or silver. In contrast, as you know, SK Creek is the most gold-rich VMS deposit, and if you've ever seen the SK rhyolite, it's strongly ceruttized QSP alteration due to the boiling of oxidized acidic fluids at temperatures below 200 degrees, creating, especially on the contact to the mudstones, this very famous sulfur salt silver gold assemblage, similar to what we see at some epithermal deposits, and we have these elevated gold, silver, and zinc contents. So I thank you again for listening, and will be able to answer any questions in a minute, but I again want to really highlight that this work was supported by Merck and Predium, and analytical analysis were done at the University of Manitoba, as well as by SGS and ALS. Thanks so much for tuning in.